thank you for the introduction. So this work is joined with Marton Horváth. So as an introduction, let me recall the definition of harmonic manifolds. So we say that a Riemannian manifold M is locally harmonic if none of the following two equivalent definitions are fulfilled. So the original definition, which goes back to Ruse, is that there is a non-constant harmonic function in a punctured neighborhood of any point P of the manifold, which depends only on the distance from P. So there's a locally defined radial harmonic function around any point. And so there are many equivalent definitions of harmonic spaces. I give another one which is important for the next of the talk, for the following part of the talk. Namely, a Riemannian manifold is harmonic if and only if small geodesic spheres have a constant mean curvature. So I say small because if you take, for example, a compact harmonic space, then as you increase the radius, geodesic spheres may lose smoothness. So up to the point until geodesic sphere is a smooth submanifold, it must have constant mean curvature. And so there are some ways to rephrase this second condition. So if we introduce the notion of an isoparametric hypersurface, so we say that the hypersurface is isoparametric if its parallel nearby hypersurfaces all have constant mean curvature. And so since in a harmonic manifold, parallel hypersurfaces of a geodesic sphere are also geodesic spheres, we can also rephrase the above condition so that in a harmonic space, every geodesic sphere is an isoparametric hypersurface. So isoparametric hypersurfaces, so for the construction of isoparametric hypersurfaces, there is an important related notion of an isoparametric function. So a smooth function is called an isoparametric function if its regular level sets are isoparametric hypersurfaces. And there is a computational method to check that a smooth function is isoparametric or not, that simply we have to compute the Laplacian of f and the squared length of the gradient function of f, and if both can be expressed as the composition of the function f with some smooth functions a and b respectively, then that function is isoparametric and vice versa. So this is about the definition of harmonic manifolds, and let me say some examples, some well-known examples of them. So it's known that every two-point homogeneous space is harmonic, and these two-point homogeneous spaces were classified by Tietz, Wang, and Szabo, and they are essentially the Euclidean space and the simply connected rank 1 symmetric spaces. So the sphere, the projective spaces over the complex hyperbolic numbers and the plane over the octonions and their non-compact duals. And also there is a non-simply connected example, the real projective plane. For a long time, these were the only known examples of harmonic spaces, and it was, well, so Lichner-Rojich conjecture only in dimension 4, nevertheless it is referred to as the Lichner-Rojich conjecture that there are no other harmonic manifolds, just the two-point homogeneous spaces. So this conjecture was proved partially by Szabo, who proved that if a simply connected harmonic space is compact, then it must be a rank 1 symmetric space. So it's one of the compact examples from the the above list. On the other hand, later, after the theorem of Szabó, Damek and Ricci found non-compact examples of harmonic spaces which are not two-point homogeneous. These are now called the Damek Ricci spaces. And actually, these are the only examples we know at present. And well, it could be conjectured that there are no other examples. The most important theorem I think we have at this moment is the theorem of Weber, who proved that if we know that the harmonic space is homogeneous, then it must be one of these examples. So it is either a two-point homogeneous space or a Damek Ricci space. So I worked with the Damek Ricci spaces in this talk, so let me briefly recall how a Damek Ricci space is constructed. So a Damek Ricci space is constructed from some initial data. First of all, we take a linear space, a Euclidean linear space S, which is decomposed into the direct sum of three orthogonal subspaces. So this is an orthogonal direct sum notation in my notes. So S is decomposed into three pieces, into the direct sum of V, Z, and A. So these are linear subspaces, and this A has dimension 1. And capital A is a basis vector there. So the Euclidean structure, so this inner product has a quadratic form, and it takes its opposite, Q, which is restricted onto Z. This defines a Clifford algebra over Z, and we should take a representation of this Clifford algebra in V, such that, so this representation will assign to every element of Z an endomorphism of V, so that if we take a unit vector in Z, then the corresponding endomorphism of V must be an orthogonal complex structure on V, so it will satisfy this condition. So once we are given these initial data, we can construct first Heisenberg type nilpotent Lie algebra on the direct sum of V and Z. So Z will be the center of this nilpotent Lie algebra, and if we take two elements of V, say U and capital V, then their Lie bracket is constructed or computed by this formula, which defines the Lie bracket in a Lie bracket uniquely. So this is in the kernel of the construction, and then using this A, we construct a solvable Lie algebra structure on S on the whole space. Where this is the Lie bracket operation. I shall not really use this explicitly in the talk, but just I wrote it to have a look at it. Well, sorry, maybe. So among the Damek Ricci spaces, we have the non-compact two-point homogeneous spaces, these hyperbolic spaces over different coefficients, so R, C, H, and the KV numbers. But all the other Damek Ricci spaces which are not equal to these are non-symmetric spaces. So they are really counterexamples for the Wigner-Ricci space. So let me tell some words about my initial questions that motivated my investigation. So if you take a non-compact Damek Ricci space, for example, a non-compact harmonic space, which is simply connected and complete, then it is true that not only geodesic spheres of small radius will be smooth hypersurfaces, but no matter what the radius is, you will get a smooth hypersurface. So And so if you take somehow a geodesic gamma and a point P on this geodesic, and you take another point which runs out to infinity along gamma in one of the two directions, either to plus or minus infinity, then for any point you can choose a sphere which is centered at that point, but the radius is chosen in that way that the sphere goes through the point P. So this way you get two families of spheres, geodesic spheres, that touch one another at the point P. They share a common tangent space, and this family of spheres, as you tend with the center out to infinity in any of the directions, will converge to two nice hyperspheres, which are called horospheres. This is a well-known construction, so this is not a question. So horospheres are properly defined in any non-compact, simply connected harmonic space. But what I was interested in is the possible continuation of this family beyond the horospheres. So if you compute so horospheres are also isoparametric hypersurfaces. They have a constant mean curvature. It's a non-zero constant which can be computed. And so one can expect that this family goes beyond. So you can construct further hypersurfaces here which somehow extend this family in an analytic way, and which also have constant mean curvature. The question is how? And if you can extend this family beyond the horospheres, then you can ask that up to what extent. So if you take this family of say, overinflated spheres, then when will a singularity occur on it, if there will be a singularity? So what kind of hypersurfaces will there? How can you define them intrinsically? So if you can define a full family that fills this gap in between the two horospheres, then there should be some hypersurface. Well, I know that there will be no hypersurface in general, but there could be some hypersurface in the middle. So what can we say about the surface in the middle we get? So it should have zero, so mean curvature, one guess. Okay, so these are the questions what I wanted to find the answer for.
I have a quick question.
Yes?
So in what sense are you interested in extending these horospheres? Would you like to find other spaces?
I would like to find a good definition for them, how to construct them, and how to study their properties. This is not an exact mathematical question, just I felt that there should be something and how to find them. And so, as an explicit example, so we know the exact answer for the hyperbolic space from classical geometry, that, so if you look at the Poincare model, then all the spheres are spheres inside the model. As you blow them up, they will converge, looking from outside to a sphere tangent to the sphere at infinity. But these spheres belong to a parabolic pencil of circles looking from outside. So you can extend this family by the remaining spheres of this pencil of spheres. And we know that these remaining spheres drawn by this brown or orange color in the figure, they have an intrinsic characterization, namely they are all parallel hypersurfaces for a hyperplane. So we can find for any such sphere a hyperplane in the. So this is drawn by blue. So for this hypersurface, you can find a plane, this blue one, so that this hypersurface is just the parallel surface of this plane. And these planes also form a nice family. They are all orthogonal to the original geodesic. And the hypersurface in the middle is just a plane itself. So it's a hyperplane, or if you like, a totally geodesic hypersurface. So we know that the answer for my previous question in the hyperbolic space, and the question is, up to what extent can we generalize this picture for harmonic spaces? So in the rest of the talk, I shall deal with the kind of toy example, the Damek Ricci spaces, because there everything can be computed explicitly, and the answer can be clarified. So now I return to a Damek Ricci space and try to find an analogous picture of the previous picture for arbitrary Damek Ricci spaces. So for our purpose, so there are several models of the Damek Ricci space. So Damek Ricci spaces can be modeled on the Lie algebra. It's a typical modelization, modeling that the whole Lie algebra of the Damek Ricci space is identified with the group itself. There is also a model on a unit ball, but for our purposes, for computational purposes, a kind of half-space model will be more convenient. So we shall identify points of the Damek Ricci space S, so it's the Lie group, the solvable Lie group, with points in the upper half space of the Lie algebra. So more exactly, we take these direct sums of V and Z, and in R we take only the positive half line, and we use this diffeomorphism for the identification. That we take the sum of V and Z, its exponential image, it will be an element in the nilpotent part, and multiply it with the exponential of the logarithm of t times A. So A was a basis vector in Gothic A. So we'll use this definition. It has some advantages. So, I mean, this logarithm has an advantage to choose the logarithm here. Now, if you use this model, then we have an explicit formula for the distance of 2 points. So if we take 2 points, x1 and x0 in the Damek Ricci space, or if you like in the upper half space with coordinates vi, zi, and ti, then the hyperbolic cosine squared of their distance half, so actually a certain function of their distance is given by this formula. It's a known formula. One can find it in text on the Damek Ricci space. And so instead, well, the distance function behaves like an isoparametric function, but it is not defined for 2 points if we move one of these points, say, to the lower half space. But if we somehow ignore this left-hand side and consider just the right-hand side, it is defined almost everywhere when we do not divide by 0. So using this formula, we can introduce kind of distorted distance function from the center x0, which has coordinates v0, z0, t0, and now t0 can be any real number. It is not just a real number from the upper half space. And we use essentially this formula, but multiply everything with t0, because we want t0 also to be equal to 0, and that division would not be nice. So somehow we forget about the left-hand side, we consider only the right-hand side function and multiply it with t0, and we look at this function just as a function on the Damek Ricci space, which depends on x0. And the crucial observation is that this function is defined for any x0, also for x0 with negative or 0 last coordinate. And so by this, so I'll call this a kind of distorted distance function from the center x0. And one can see that the level sets of this dx0 are ordinary geodesic spheres when this center x0 is in the upper half space, when its last coordinate is t0. When the last coordinate is t0 is 0 for x0, then the level sets will be horospheres. So in some sense, if you look at the level sets of this function for an x0 for which t0 is less than, t0 is negative, then one can expect that these will be exactly those hypersurfaces that can fill the gap between two horospheres. So actually, if we look at the function dx0, then no matter what the last coordinate is, they will always be isoparametric. So their level sets will be indeed isoparametric functions. And this can be checked by a computation which computes the Laplacian of dx0 and this the squared norm of dx0. So no matter where x0 is, both the Laplacian and this can be expressed as a function of dx0 itself. So this is really an isoparametric function. Usually isoparametric functions have a nice structure proved by Wang. So to speak about this function structure, let me introduce what a focal variety is. So a focal variety of an isoparametric function is one of its singular level sets. And there is a theorem by Wang that if we have an isoparametric function f, like connected complete Riemannian manifold, then such a function can have at most two singular values, its minimum and its maximum if they exist. So, and it is also known that if you take any of the focal varieties corresponding to these minimum or maximum values, then all the regular level sets will be tubes around the focal varieties. And the focal varieties are known to be minimal submanifolds. And of course, all the other level sets will have constant mean curvature. So to understand the structure of this function, or the level sets of this function dx0, as x0 has negative last coordinate, we have to look for its focal hypersurfaces. Or in fact, it has only one single focal hypersurface. Namely, so the minimal value, so dx0 will have non-negative values, and the only singular value of it will be 0. And the equation of the corresponding focal variety is this equation. So more exactly, it's a system of equations consisting of two equations. So if you look at this first equation, it's an equation for the v plus a component, and this equation defines from the outside, so it's not an intrinsic description, but an extrinsic description. So this is a paraboloid of rotation in the AV plane. So if you look at the solutions of this equation, and the second equation is just a way to express z as a linear function of v, inhomogeneous linear function v. So for any point on this paraboloid, you should add the z coordinate, which depends on v linearly. So you get a kind of affine image of this paraboloid, which is also a paraboloid looking downward. Its top vertex will be at V0, Z0, negative T0, and so it will intersect the boundary hyperplane of our model, which we can call the hyperplane at infinity in an ellipsoid. So this is how our focal surface looks like in this example of the focal variety. It should be mentioned that it's a submanifold whose dimension is equal to the dimension of V, so of this V. So it's not a hypersurface. So it's difficult to draw in the figure something which is in between a hypersurface and a curve. But this is a submanifold, and so intrinsically it is a minimal submanifold whose dimension is equal to the dimension of V. So all the other level sets will be cubes around this. So we have the candidates from which we have to choose the extension. So we have had originally this blowing up. So the picture of these blowing up spheres tangent to one another at one point, and we want to find the extension of this family. So we know from which family we should choose, but there are too many of such. So actually, to find the right cubes from the extension, we use an extension of geodesics. So geodesics are described in Damek Ricci spaces. So again, this is a well-known formula. So for simplicity, we take a geodesic which goes through the unit element of the Damek Ricci space. If we know geodesics through the identity element, we can describe any other geodesics by a left translation, because Damek Ricci spaces are. Left translations are affine transformations from outside. So the picture we have at E, so if you have an affine invariant description of the geodesics here, then it will extend to any other point in S. So, well, here's a formula for a geodesic where this parameter theta is actually, so in the place of theta, we have to write the hyperbolic tangent of t over 2, where t is the arc length parameter on the geodesic. So this hyperbolic tangent t over 2, it is a function which takes values in the interval negative 1, 1. And if we let t run over from minus infinity to infinity, then this value, which is essentially theta in the next slide, so this value theta will run only minus infinity, so only from minus 1 to 1. But in fact, this formula gives you a properly defined point, maybe outside the upper half of space, for any theta. So if you let theta run over all real numbers, then this will give you a point, not in the upper half, not necessarily in the upper half space, but maybe something below. And actually, there is also a well-known, an easily computable limit of this if we let theta converge to infinity. But in that case, the limit can be a point at infinity. Sometimes it is a finite point, sometimes it is a point at infinity. But anyhow, so this mapping gamma can be extended to a map from the real projective line into the projective space obtained from S by adding points at infinity. And so if you look at gamma, then its coordinate functions are rational functions, and this will be a rational equivalence from the projective line onto a in most cases onto a conic section. So the image will be either an ellipse or a parabola, or sometimes it degenerates to a straight line. But whenever it is a parabola or a straight line, whenever it's not completely contained in S, but converges to a point at infinity, then it will always have the same point at infinity, namely the point at infinity of the a-axis, of the vertical axis, and I'll denote this point at infinity by this strange asterisk sign. So in our model, if you take extended geodesics, they will be just these conic sections. So actually, this means that if, say, our geodesic, or original geodesic extends to an ellipse, or maybe to anything else, then, so this is a natural choice for the family of surfaces. So we let theta run over the projective line here, and for all points theta on the projective line, we take this sphere-like object which is centered at gamma theta, which is some point in the lower half space, and we choose the constant here so that the sphere goes through the point P. And so this is a properly defined full family if gamma is an ellipse, because then we'll have no points at infinity on this, on the extended gamma. But when gamma extends to a parabola or to a straight line, then so there will be one case when gamma theta is a point at infinity, and for the case when gamma theta is a point at infinity, this surface d gamma theta is not defined. So somehow we get almost the full family we were hunting for in all cases, but in the parabola and straight line cases, there could be one missing surface, which we want to determine in the next slide. So actually, these missing surfaces can be computed by taking a suitable normalized limit. So it turns out that if you look at this distorted distance function for gamma theta, so if gamma theta converges to infinity, then this whole function will blow up. So everything will go to infinity. But if simultaneously we normalize this function, we divide by a constant which depends on theta, and so with this normalization, we take the limit of the function d gamma theta, then there will be a nice limit function, maybe this one, and this limit function will also be an isoparametric function. It will have a focal surface, but the focal surface for this is not a downward-looking elliptic paraboloid like in the ordinary case, but it will be so from the outer view, it will be a linear subspace of, or an affine subspace within the upper half space. And this, so the direction space of this focal variety, so it will be just a vertical space. It will be given by this formula. So if this is, for example, a parabola, and it's at the top vertex, its tangent vector is v, then so this focal surface will be the kernel of the adjoint operator of v intersected with the hyperplane perpendicular to v. And so with this direction space, we should take we should translate this through p, so the top point of the parabola, and that will be the focal surface when we take the top In the case when gamma is a vertical line, so it's a degenerate case, then this limit, so this limiting function, so the limit of this function on the right-hand side, which I denoted by d gamma star, it will have no focal variety, and its level sets are just horizontal hyperplanes, and they are just horospheres, so it's not an interesting case. There is, yeah. So actually we have the full picture. So here, in this figure, we have a geodesic. Now in this case, it's a kind of ellipse. So if we pick a point here on the upper part, somewhere, then you can ask where to choose the center if you want to get the focal surface of dx0 to go through this point. And there is an elementary geometric description for this, that so this geodesic as a conic section looking from outside intersects the hyperplane at infinity at 2 points, and we also have this given point and the center we look for, and so these 4 points on the body should form a harmonic range, which means that the equostation should be -1. So if you want to get a focal surface through this point, you should take its harmonic pair relative to the intersection points UV and take the function, the focal surface of the function dx0, and it will give you this focal surface. And so these focal surfaces will move along gamma. So for each point you will find an orthogonal focal surface, and parallel surfaces of these focal varieties can be used to construct the family of isoparametric hypersurfaces that we'll look for at the very beginning. Oh, so there was one more slide I wanted to tell. So if you take one focal surface, or focal variety, one of the focal varieties, which intersects gamma at this point, and it corresponds to gamma. Yeah. Then, if you pick another geodesic, which meets this focal variety orthogonally, then so it can be checked that this geodesic will also go through the same point x0, and actually so if x0 is an ordinary point, it's not a point at infinity, then all geodesics that go through x0 will meet this focal surface orthogonally. So geodesics running out from x0 orthogonally, they all meet at x0, and vice versa. So any geodesic which runs through, whose extension runs through x0, they will meet this focal variety orthogonally. But when we computed these limiting focal surfaces, then I haven't mentioned at that point, but the limit will depend also on the way on gamma. So it depends not only on the center, which is a point at infinity, but it also depends on from which direction we approximate, in which direction we converge to this point at infinity. So that's why we introduced the notation d gamma. So gamma is introduced there. And so it turns out that a similar picture as here is not true when x0 is the point at infinity in the a direction. But it is not necessarily true. But so whether it is true or not depends on the so-called J-squared condition, which was introduced by Colling, Dooley, Polanyi, and Ricci. So it says the following, that we say that the Damek Ricci space satisfies the J-squared condition if for any two elements of Z which are perpendicular and any element of V, we can find a third element of Z for which this equation is fulfilled. Well, it is known that Damek Ricci space satisfies the J-squared condition if and only if it's one of the symmetric Damek Ricci spaces. And it turns out that, so the picture I drew here for an ordinary focus surface, that all the geodesics meeting orthogonally this focus surface, if and only if they go through x0. So we'll extend to the case of the point at infinity, if and only if our space satisfies the J-squared condition, which is equivalent to being symmetric. So thank you for the discussion.
So are there any questions?
What is known about not homogeneous harmonic spaces?
So it is not known if they exist. At least I don't know any example. But
There's no
so-
other example.
so I have only feelings that I guess that this family of spheres can be extended at least for a short time beyond the horosphere. But probably, well, here as well we have a singularity just in the middle. So as you extend, there in the middle there will be a focal variety which drops its dimension. But maybe for a general harmonic space, this singularity can appear sooner. And my plan is to understand or try to tell when this singularity will appear. So this can be, I think, told on the basis of the. So every harmonic space has a characteristic function, the volume of how the volume grows for
So
the volume density function.
At least,
I think in terms of
locally non-complete, you believe that they can exist, or not?
I mean, you ask the existence. I don't know. Maybe they exist, but it's so. Just it's hard to construct non-homogeneous examples. So I wouldn't be surprised if they would exist.
I think my question was part of that. But so, would you think the technique you use to complete the space between your spheres here in Damek Ricci, extended outside, and how can that be used for? Do you think that can be applied to complete this linear reconstruction somehow? Space where there is still open?
So the idea is that somehow something will happen here. So if you find where the singularities will happen, or if you can say in general that they will always be a kind of, what can you say about the focus surfaces in general? So for example, here the focus surfaces have dimension V, or the dimension of V. So something is encoded in the geometry of the focus surfaces. And so maybe this geometrical picture can understand something.
And because it's trying to use this for sphere type and the behavior there, trying to confront this with neural conjectures and
it was also a surprise for us that when you look at these focal surfaces that intersect the geodesic orthogonally, that there is a distinguished one whose center is a point at infinity. So somehow they are not the same, also from the intrinsic picture. So it would be nice to understand a similar picture in a general harmonic space, but we are not at that level. But I think explicit examples are good because if we know what the truth here is, then we don't try to prove something which is not true here.